Okay, so the previous lecture I talked about the concept of frequency response, and we also talked about the Bode plot and how to plot a Bode plot or Bode diagram for very simple first order systems, and also transfer functions that are just the combinations of bunch of first order transfer functions, or rather first order polynomial. So in this lecture, I'm actually going to discuss how to draw the Bode plot for second order systems. I'm also going to show you an example if you have a combination of first order and second order system, then how do you go about drawing the Bode plot associated with those kind of systems. So here you see that let's just assume that you have a very simple second order polynomial s squared plus 2 zeta omega n s plus omega n squared. And of course, if you just replace s by j omega, it would be just j omega squared, which is negative omega squared, plus 2 zeta omega n j omega, that's what you see here, plus omega n squared, that's what you have here. So now really g of j omega just becomes omega n squared. So that's actually going to become your real part. So that becomes your real part, and this actually becomes your imaginary part. So now the magnitude of the polynomial g at j omega in terms of the decibel dB is going to be 20 log in the scale of 10 of magnitude of this g at j omega, which is going to be square root of omega n squared minus omega squared plus 2 zeta omega n omega squared. And also the phase angle is going to be the arctangent of the imaginary part, which is this, divided by the real part. So now what you can do is actually to plot this magnitude in dB and phase angle in terms of omega. But we also learned that instead of plotting the actual magnitude and also the phase angle, instead we can just draw what is called the asymptotes, or just simply straight lines. So previously for first order, we saw that if there is going to be an increase or decrease, it is going to be with a slope of 20 dB per decade for the magnitude in terms of dB, and for the phase angle, the slope is going to be 45 dB per decade. Well, either positive or negative 45 dB per decade, depending on whether it's s plus, let's say, omega, or 1 over s plus omega. But now for second order systems like this, so it is actually going to start flat at, in this case, it's just going to be, so now what you see here, so the magnitude is really going to be, if you just put s to be 0, so that's just going to be 20, or just simply here. So if you just replace omega by 0, so it's just going to be 20 log of omega n squared. And of course here what you see is actually in 0 dB, because this is actually a scale. So now you see that's 20 log of m omega n squared. So really if you just scale it by the factor of omega n squared, then it's just going to be 0 dB, because that's just going to be 1. Otherwise, this line, the magnitude is really going to be associated with 20 log of omega n squared. And then at one point it's going to break. So if you remember, it was just what we call break frequency. So for the first order system, if you had s plus omega, that break frequency would be omega. But now for second order system, that break frequency is going to be this omega n, which is what we call the natural frequency. So the break frequency of the straight line approximation of the Bode plot is just going to be omega equal to omega n. So now, and again, even the horizontal axis, it's also scaled by a factor of omega n. So really omega is equal to omega n, that's going to associate with this break frequency. Then it's going to break and it's going to go up, and it's just going to ramp up at the slope of 40 dB per decade. So it's going to be 40 dB because we actually have a factor of s squared. So for first order, the slope of this line is going to be 20 dB per decade, but now for second order, it's going to be 40 dB per decade. That's what you see here. So now for phase angle, always remember that it's going to start flat. So for example, if you just assume S is equal to 0, so your G at 0 is just going to be omega n squared, which obviously is a real number, and therefore the phase angle is just going to be 0 degrees, and that's what you see. And when omega is very large, then you just have G of S equal to, so these terms actually become dominant compared to the other terms, and therefore we can just approximate that as at very high frequency. We can just approximate these second order polynomial by just simply S squared, and when S is j omega, so it just becomes negative omega squared, which is obviously a negative real number whose phase angle is going to be 108 degrees. So anywhere in between the slope of the line, well, it's just going to increase by this line. So now, just like the first order system where we had two break frequency, one would be the 1/10 of this break frequency, and the other one would be 10 times this break frequency. We're actually going to see exactly the same thing here. So now, the first breakpoint associated with the phase angle is going to be 1/10 of omega n, which is exactly the same, natural frequency as before, and right here, this is going to be 10 multiplied by omega n. So now, again, here the slope of this line is going to be 40 dB per decade, but here you see that the phase angle goes from 0 degree to 108 degrees in 2 decades, and of course in the dB or in the log scale, and therefore it's going to 100 over 2 degree per decade, or 90 degree per decade. So remember, for first order system it was 20 dB per decade and 45 degrees per decade, but now for second order like this, it's going to be 40 dB per decade and 90 degree per decade. So now, actually it turns out that if you plot the actual frequency response of a second order polynomial like this, well, I mean, you just saw that for a straight line approximation, it would be just flat and just go up 40 dB per decade, and for phase angle it would be flat, goes up and flat again. But now the actual response, it's actually going to look like this. So it's, I mean, still you see that the asymptotic approximation is going to, so you just go flat and just go up with the phase, with the slope of 20 dB, well, 40 dB per decade. But now it turns out that for magnitude, or in terms of the dB, the Bode plot, it's actually look very interesting. So it is going to be dependent on the value of zeta, and you remember the zeta, the damping ratio. So it turns out that if your damping ratio is greater than 0.707, which is actually going to be right here, so it is going to come, okay, so if it's greater than that, it's not even going to go below this flat line, just going to go straight, just going to reach this, what we call high frequency asymptotic, and this is the low frequency. So if zeta is greater than, in fact, this is the point, so somewhere here, so this point right here is actually associated with zeta equal to square root of 2 over 2, which is 0.707. Okay, so now it turns out that if you're below this value, then your response is actually going to show, you can call it an undershoot or overshoot. So it's actually going to look like, so it comes down and it goes back up. Whereas if your zeta is greater than this value, then you're just going to go straight, going to converge to the high frequency asymptote. And it also turns out that this value of the peak, this value, so basically where this plot is minimum, well, for this one is minimum, for the next one that you're going to see, if it's maximum, it's also going to be dependent on the value of zeta. And again, in the next slide, I'm actually going to show you some more details. And the same thing for the plot, for the phase angle plot. So it does actually look like this. So the closer you are to zeta equal to 0, which means completely oscillatory system, then it's actually going to look like this. But now as you increase the value of zeta, it actually gets closer to what we saw in the asymptote. So now if the value of zeta is larger, then the response is kind of closer to what we saw before. So now if you remember if you remember for second order system, well, actually for second order systems we often have them in this form, which is, well, actually, well, technically speaking, this is not correct. So it's supposed to be omega n squared in the numerator divided by this. So now this would be your standard form second order system, which obviously has two poles. So now if you plot the frequency, well, the Bode plot for this one, it's just going to be an inverted flip version of, well, an inverted version of what you saw in the previous slide here, just with respect to the horizontal axis. So it's just going to be inverted with respect to horizontal axis, and that's what you get. So now, as you see, this value of the peak in the Bode plot, the Bode plot magnitude response is actually going to be, the value of peak is going to be maximized when zeta is going to be equal to 0. But now as you increase the value of zeta, then the peak is actually going to decrease. And when your zeta is less than 0.707, then there is not going to be a peak. So you see that does not really show a peak. So it's just going to come down straight. Okay. And the same thing for the phase angles. You know, we actually saw something similar in the previous slide. So this is just going to be an inverted version of that with respect to the real axis. Okay, so here you see some more details about the Bode plot, particularly the Bode plot, the magnitude of the Bode plot in terms of dB. So now, if you have a second order system in this form, GS equal to omega n s squared divided by s squared plus 2 zeta omega n s plus omega n squared, which was the standard representation for a second order system. So if you plot this response, it looks like this. And of course, remember that the slope of decline is almost negative for dB. Well, it's not, because this is not really going to be perfectly aligned, because this is more realistic than just simple straight line or asymptotic approximation. So if you just plot this, it's approximated the slope of this line. If you can approximate it by line, it's going to be negative 4 dB per decade. But if you remember, there was going to be a peak, and there was also going to be there's going to be a frequency associated with this peak, and there's also going to be a peak value. So now, or peak gain. So now it turns out that if I go back, now the way these equations are actually derived. So if you remember these, so now if you just try to maximize this magnitude in terms of dB by just taking a derivative of this guy and make it equal to 0, then that's obviously going to give you a value of omega, and associated with that value of omega, if you just plug it back into this equation, you're going to come up with the value of dB. So now, if you do that, then it turns out that the equation for this peak, or the peak frequency, which is what we call resonance frequency. So this resonance frequency is going to be omega n square root of 1 minus 2 zeta squared. So now, if the value of zeta is very, very small, then omega r is actually going to be approximated by omega n. But then you see, I told you that there was going to be a peak. If you just go back here, You see, I told you that there was going to be a peak only when the value of zeta is greater than or equal to 0.707. And where does that come from? It actually comes from exactly, it actually comes from exactly here. So now when you do all this math, your omega n is omega r resonance frequency is going to omega n square root of 1 minus 2 zeta square, which is going to be only meaningful if 1 minus 2 zeta square is greater than or equal to 0, and therefore zeta square is less than or equal to 0.5, and therefore zeta is just going to be, so now zeta is just going to be less than or equal to 0.707, which means that if you have this value, if you have a value of zeta which actually satisfies this condition, then there is going to be a peak, and that's something that you can actually confirm here. There is a peak, but if the value of zeta exceeds 0.707, something like here, that's like 1 or 1.5, there is not going to be a peak. And then, so now basically this would be the resonance frequency, which is going to be this frequency right here. And then corresponding to this frequency, you also have a value MR, which, remember, so this is not really going to be in dB. So this value is not in dB, and the value is just going to be 1 over 2 zeta square root of 1 minus zeta square. And this is what we call the peak frequency. So this is the peak frequency gain. So that's going to peak frequency gain. Remember that this value that you see here, that is only assuming that your starting point is 1 dB, and it means that you are looking at this transfer function in the very standard form, which means that if your transfer function, your second order transfer function it's not in the standard form, then this MR will have to be scaled by whatever the DC gain is. So the DC gain here is just omega n divided by 0 plus omega n square, which is 1. But if it's not 1, then you're actually going to have to scale this omega r, which is the peak frequency gain, by that non-unity DC gain factor. And I'm actually going to show you an example, and that example just going to have some details about how to do that scaling. So now, if you're going to ever use MATLAB in order to plot the Bode diagrams, if you just simply use this command BODE, Bode, and of course, so all you need to is just to say Bode, num, and then, and num is just your numerator polynomial, and then is just your denominator polynomial. It automatically plots two subplots. The top one is going to be the magnitude in dB, and the bottom one is going to be the phase angle, of course, in terms of the degree. So, but if instead of Bode you just use another command, Bode mag, it's only going to plot the magnitude in dB. Right. So next I'm going to show you an example on how to draw a Bode plot when you have a combination of first order and second order systems. So in the previous class or in the previous lecture, you saw how to draw a Bode plot when you had just a combination of first order systems. So now here you have 2 first order and 1 second order. So now you have 1, 0 at -3, which is obviously first order, and then another first order, which is the pole, -2. And so you also have a second order, which is in the denominator. So now, remember that for every first order, when you're trying to figure out the magnitude diagram, for every first order, you're going to have one break frequency. For every second order, you're going to have also 1 break frequency. But if you have a phase diagram that you're actually trying to figure out, for every first order, you're going to have 2 break frequency, 0.1, and also 10 times whatever, for example, this value is 3 or 2. And for second order, you're also going to have 2. But those are actually going to be 1/10 and 10 times natural frequency, which for this example, omega n squared is equal to 25, and therefore omega is going to be 5. So now we have a pole at 2, we have a 0 at 3, we have an omega n which is equal to 5. So you see that for pole at -2, it starts flat up to -2, or up to rather 2 radian per second. And since it's a pole, then after that it's just going to drop. It's just going to continuously decrease at the slope of negative 20 dB per decade. For 0, initially it's flat up to your break frequency, which is 3, and then after that it's just going to go up at the slope of positive 20 dBs. And for omega n equal to 5, which represent the second order, initially it's flat, and then at that omega n, at that frequency, that break frequency of 5, it's just going to go down, because this is a second order, but that's in denominator. Okay, so since it's denominator, after the flat part is over, it's just going to drop the slope of -40. So now for each of these parts, if you just add these 3 numbers, you're actually going to get the slope associated with each of these. Well, I mean the total slope associated with each of those segments. So now it means that before 2 radian per second, it's flat. Between 2 and 3, it's going to decrease at the slope of -20, and at 3 it just becomes flat up to 5, and at 5 it's just going to simply drop at the slope of -40 dB per decade, and that's something that you're actually going to see in the next couple of slides. So for the pole, what you do, you have to actually consider 1/10 and 10 times of each of these numbers, in particular 2, 3, and 5. 1/10 of 2 is 0.2, 1/10 of 3, 0.3, 1/10 of 5, 0.5, 10 times 2 is 20, 10 times 3, 30, 10 times 5, 50. So for pole at -2, so basically it's initially 0 degrees. At 0.2, it's just going to decrease at the slope of -45 degree per decade, and 10 times 0.2, which is 20, it's just going to go flat again. That's why you say -45, -45, -45, -45, and after 20 it's just going to become flat, because it's actually going to reach -90 degrees. And so you can actually figure it out the same way, but since this is 0, it's going to increase this slope, and it's just going to drop flat. And omega n equal to 5, since it's also, well, since it's second order and it's a denominator, it's going to from flat, it's going to drop to the rate of, to the slope of -90 degrees per decade. And 10 times omega n, which is going to be 50, it's just going to drop flat again. So if you just add all these slopes, then these are actually going to be the numbers. So in fact, for example, if you plot s plus 3, it's actually going to start from this point at omega equal to 3, it's just going to go up, it's just going to break and go up, slope 20 dB per decade, and the phase, so for the phase angle from 0.3 to 10 times 3, which is 30, the slope is going to be positive 45 degrees per decade. So now one thing that you have to be careful about here is that this point here is actually 20, this flat magnitude is 20 log of 3, which is somewhere like, I would say log of 3 is 0.47, 20 log of that, so that's like 9.5 dB. So this is really almost 9.5 dB, which is somewhere in between 0 and 20. So now for 1 over s plus 2, initially starts, and then it's going to drop at this frequency 2, and the slope of the drop is -20 dB per decade. So the same thing here, you start from 0, eventually arrive at -90 degrees. Slope of this line is -45 dB per decade. So for second order, if you really want to show some more details about this second order system response, since it was 1 over s squared plus 2s plus 25, then omega n is 5 and zeta is going to be 0.2. Since zeta is less than 0.707, then there is going to be a peak. Okay, something that you see here. But now you can find what is the resonance frequency using the equation omega r equal to 5 square root of 1 minus 2 zeta and 2 zeta square, which is going to be 4.8. So now you see that in your asymptotic or straight line approximation, your break frequency or your peak will actually occur at omega equal to omega n, but actually it is not omega equal to omega n, it's omega equal to omega r, which is 4.8, which is still pretty close to omega n equal to 5. So that's going to be this point. So if you're also interested in knowing what is the magnitude, so again, if you start flat, so the magnitude here is going to be 20 log of 1 over 25, which is going to negative 28 dB, which is this point. So it's just going to start flat and just going to go up. There's going to be a peak and you come back down. And the slope of this guy is negative 40 dB per decade. So now, if you remember, for the value of the peak frequency gain MR, the equation would be 1 over 2 zeta square root of 1 minus zeta square. But that equation was valid only when you have the system in the standard form, which is if you have the 25 here, you must also have the 25 there. If you do not have that, then all you need to do is just to take this number and scale it by this value, which is the DC gain 1 over 25. So now really your new peak is going to be MR equal to this, and it's going to be almost 0.1, and 20 log of 0.1 is really negative 20 dB, which is going to be this point here. So this peak value here is really almost negative 20 dB, and that happens at this frequency, 4.8 radian per second. So now basically you need to take this plot, you need to take this magnitude, add it to this magnitude and also to this magnitude, so that will actually give you the complete magnitude plot. You can also take, for phase angle, you take this one, you add it to this one, and you also add this one. And of course, remember that for each of these, there is actually going to be a break frequency. Actually for Bode, there's going to be, for the magnitude, there's going to be one break frequency for each of those. So really combined, you're going to have 3 break frequency. But for the phase angle, we're going to have 3 multiplied by 2, 6 break frequency. So if you just combine all these 3 plots, you see that it starts flat. Then at some point, it's actually going to drop. So now you see this is 2 radian per second, this is 3 radian per second. And we said this is 5, but really this should be 4.8. So 2, 3, 4, 5. So really that point in which the plot breaks is not really 5, because this is just the asymptotic or the straight line approximation, but this is the actual one. This is the actual one. Okay. So the curve that you see using the black line, so this is actually the actual Bode plot. Anyway, so you have so after this flat part is over, you're going to drop negative 20 dB. And after that, it becomes flat again, and after that, it's actually going to drop negative 40 dB per decade. And that's also something that you can figure out here. It's initially flat, then it drops at It's initially flat, then drops at negative 20 dB, then it becomes flat again, then it drops again at negative 40 dB. And that is exactly what you see in the final response. So for the phase angle, it's also the same, but of course, for the phase angle, you're actually going to have many more. You're going to have 6 break points. You're actually going to have 1 here, then 1 here. So you see that you're going to 1 here, 1 here. That's 2, that's 3, that's 4, 5, and 6. So combined, you're actually going to have 6 break points, and these you could even have figured it out using this. So now, initially you're flat, then negative 45 degrees per decade, then flat, then negative 90 degrees per decade, then negative 45 degrees per decade, then again negative 90 degrees per decade, and eventually it just becomes flat. And this also confirms exactly what we just start flat, end with flat, and in between you just go up and down. Well, basically.